Hello, my name is Khazra Tarek. My paper is about radial self-calibrated network with multi-scale channel attention for accurate EOG-based eye movement classification. This paper is taken from IEEE Journal, which is published in 2024. The research background, the EOG technology. The EOG means the electroencephalography measures eye movement by recording electrical potential differences around the eye, used for tracking eye movement in various conditions such as uh, medical diagnosis, human computer interaction, or any kind of assessments or a conjugative assessments. Assistive technologies are those technologies which empower the individual with the mobility by enabling them to interact with computers, such as controlling wheelchairs, operating robotic arms through the eye movements. This makes EOG the vital role in assistive technology for people with disabilities such as ALS or electrical paralysis, or also having the spinal cord injuries. There is another technology existed with the EOG applications, which is hand-free control applications, such as EOG allows hand-free control of devices, which is valuable for situation where user cannot use the hand, such as driving, surgery, and virtual reality environments that the user can select on a screen, scroll down, text, play games by moving their eyes by using the patterns of eye movement. Another technology is about gaming and environment. In gaming, EOG use impressive experiences where the eyes of the users or a player movement control the characters or navigate through the game environment. This I add the new layer of interaction, make the game more intuitive and engaging. EOG play an important role in augmented and virtual reality as well, where the user interact the virtual world specified by using their eye movements. This technology could enhance the realism to these impressive environments and allow the user to select the menus, switch on off by the visual environment without using their hands and control their head controllers. EOG systems had used HCI research to control the user conjugative load attentions and emotional states by tracking eyes movement during the tasks. These intents has high helping in designing more user friendly interactions, adopting systems to users' behavior and under controlling how the users interact with the various softwares. EOG signals in human-computer interactions used to interrupt the eye movements that allow the users to control the interface and application without using the need of traditionally kind of input-output devices like a mouse and users. This is specifically useful for the accessibility games, accessibility technologies, and the more user experiences. EOG signals are often contaminated by the noise from facial muscles, electronic interference, making the classification more difficult. More accurate eye movement classification from EOG signal requires reversed algorithms to filter other interferences, are prone to communicate from the noise such as muscle movements, facial expressions, and other electronic interference, which can communicate accurate detection of eye movement. Designing algorithms, noise, major technical challenge. EOG systems often require the calibrability to ensure the accuracy in tracking eye movements, such as the users have a different baseline potentials, and these differences must be accommodated by the system design. Self-calibrated models or systems that adopt to these variations are being exploited by EOG using users friendly. EOG does not offer a precise resolution as optical systems like infrared eye trackers. It detects the eye movement direction, horizontal and vertical, but not the fine-grained location of the gaze eye's movement. As this diagram below illustrated the basic principle of EOG, which measures the eye movement by detecting the eye potential differences around the eyeballs. This is the left eye, which eye autonomy and an electric dipole. This is the right eye, and this is the eye right side of the electric dipole. I, as an electric dipole, act as a dipole which electric potential differences between the front cornea and the back retina. The front cornea means the positive charge. This is the positive charge. And the back retina means the negative charge. The charge differences generate the potential fields that shift the eye move. The eye movement, which eye moves to the left as shown in the diagram, you can see that positive cornea moves towards the left side of the face. It's moving toward the left side of the face, this one, and causing the change into the electrical potential, which can detect the electrode changed to the eye. And this is the electrode placed around the eyeball to detect the voltage of changes the eye movement. Electrodes A is the place where the outer side of the eye is sensitive to the horizontal eye movement, and electrode B is placed over the below the eye, which capture the vertical eye movements. So electronic signals of EOG produced, these electrodes are presented by the waveform of right side. The wavelengths are corresponding to the changing in eye's position, which eye moves in a specific direction and detected the shifts of electronic potential, producing the signals that can be easily shifted to the EOG signals. The traditional approaches for eye movement classification refers the techniques used to classify the interrupt of eye movement data, such as fixation, blinds, and sasides, from the signals of electrography and optical-based eye tracking. Before raising the deep learning and machine learning to the various processing features, and the machine learning techniques are used to classify the eye movements. These methods, the traditional methods, are basically predefined thresholds to distinguish the different types of eye movement based on parameters like velocity, acceleration, positional changes in eye signals. It identifies when the velocity of eye movement exceeds with a certain threshold with a fixation which the eye is relatively still, and detected with the velocity drops below as a threshold for a gain period before the classification system. Processing techniques like low pass filtering and a high pass filtering are applied to move noise, isolate specific frequency which is related to the eye movement. Traditional machine learning algorithms, which are applied on extracting features from EOG eye tracking data to classify the different eye movement transformations. Later, the machine learning methods emerged, which relied on handcraft features such as multi-scaled temporal characteristics and extracted from EOG signals as well. Machine learning methods may be criticized for the resilience on the domain specific knowledge, requiring significant manual effort in future engineering. This is the limitation for the developing more automated features extracting the technique from deep learning. As the diagram shows that the machine learning classifier is an eye tracking system used in visual reality environment for the user identification, where the participant is interacting with a virtual reality. This is the participant, and it is participating with a virtual reality, and the critical image. The user is in a virtual reality scene, and the eye movement are tracked by the eye tracking devices systems integrated with the virtual reality headset. The particular likely looking to the various object into the various space, such as text or grass or that solar some the panels, and the greenery and the person standing in between them. The eye tracking data include the information about users' gaze direction, fixation, possibly blinkness, and eye quicking movements, eye movements up, down, right, left, and right. So the machine learning classifier trained to recognize the specific pattern into the eye movement data, which are unique to the each every participant is a different. This model used the algorithm like a sport vector machine, random forest, or a neural network identifications to distinguish the users behind their eyeball behavior. Deep learning, particularly CNN and other deep architectures, have shown significant potential automatically leaning features such as raw signals, making it a suitable approach of EOG classifications. Research likely covers the uses of CNN and other architectures in psychological signal analysis is often represented as 1D or 2D time series of signals of CNN, convocational layers to protect the data like blink and fixations. Filters such as kernel slides over the input data detections, local features like peak or flat regions, which are rapidly eye movements or fixations. Multi-layer of convolutions are pooling, which is downsampling layers are lean, increasing complex representation of eye movement data, which combines the features extraction capabilities with the temporal sequences of modeling of RNN and CNN. The EOG signal is the first pass-through of series of convocational layers to the contract of meaningful features for the raw data. The output of the convocational layer is to feed the recurrent network to the capture the temporal differences of time steps, which the early DL models, such as the say single scale, which is convocational neural models, posed to be the accurate 90.47% complex of EOG patterns. Additionally, in 2017, the single scale CNN decoding the eye movement during the reading task, obtaining the impressive accuracy on subject specific training. As the diagram illustrates that the basic principle of electroholography, that how the eye movement by recording the electric potential around the eye. The left side, which is the cornea, the presentation and a transparent of outer side of the eye. This one is the cornea, which is the outer side of the eye, and the retina, which is the right and a light sensitive layer at the back of the eye that receives the visual information and sends the signals to the brain via optical nerve. There is an electrodes which is provided by the electronic potential. The human eye interacts like dipole with positive charges at the cornea and the negative charges at the retina. This is the natural voltage differences which the EOG exploits to the measuring of eye movement. The right side of EOG circuit, this one is actually the signal detection, where is an electrodes at the left bottom side and electrodes at the right top side are placed around the eye to detect the electronic potential generated by the cornea retina dipoles. Typically, one electrode is placed near the outer corner of the eye, which on the skin you can say, or inside the skin on near to the eye, or an other electrode is placed to the outside, which for the horizontal movements and the vertical movements as well. When the eye moves, the positions of the cornea and retina change respective to the electrodes. This shifts in position cause a change of electrical potentials, which is recorded by the electrodes. For example, if we can say that when the eye move left side, so, or the light side, the cornea moves toward the positive charge, which will move toward the more closer to the electrode, and the retina is on a negative charge, which more closer to the other electrode. So, generating with the measurable voltage differences. what the electric circle the circuit diagram specified, that there is a resistors and wires which presents the pathway through which the electrical potential is measured. The voltage differences across the electrode is amplified by presenting a triangle diagram, this diagram, which enhance the signals, which shows how the cornea and retina dipole generate a measurable electrical potential which eye moves. The electrode placed around the eye capture this voltage which changes based on the movement of eye. Let's talk about the problem statement. Low classification accuracy for the complex eye movements. Existing EOG-based classification method struggles to extract the high-quality discriminative features for accurate EMC. While the traditional methods for EOG-based the eye movement classification face the significant challenges in accurately classified multi-eye movement patterns. While single patterns like blinking or bidirectional movements can be classified with threshold-based approaches, classifying complex and multi-movements remain the difficult due to the mutual calibration requirements and individual variability. The challenge is to capture the diverse eye movement pattern using the EOG, which shows the multi-scale morphology. Handcrafted features in ML is a limitation to this paper. That machine learning approaches heavily depend on the handcrafted features to require the prior knowledge to the effective to the machine learning features. These features, such as multi-scale or temporal characteristics, are often obscure and fail to recognize and generalize with the well different subjects and environments. There is a need for more sophisticated deep learning architecture that can handle multi-scale features and adapt to the varied conditions for EOG signals which maintaining the computational efficiency. So how can to design the deep learning architecture that improves the accuracy and robustness of EOG based EMC, which is eye movement classification? Effectively challenging of a noise, variability, complexity in EOG signals. So there is a problem or the question that how the multi-scale challenge attention module adaptability weight features to map the different scales. The residual calibrated network in multi-scale channel attentions proposes the novelty of a deep learning architecture that can account for the variations of EOG signal across the different subjects and conditions. MCA mechanism capture the features at a different scales, allowing the network to focus on most relevant information or into the EOG data while filtering the out noise and irrelevant signals. Even though the EOG signal contains the multi-scale features that differs in irrelevance of classification and existing data deep learning frameworks that do have to differentiate between irrelevant and relevant features on different scales, which enhances the learning processes by preventing the low level features and improving the gradient flow, leading to the more appropriate classification results. As the results, they can end up with the capturing the redundant of noise and negativity effective in classification accuracy. Need for the efficient and adaptive feature refinement. In real-time applications of human-computer interaction, computational resources may be limited. For the fast processing is essential. Models are too complex and insufficient suitable for the real-time use. The need of efficient and adaptive features refinement in an EOG-based movement Classification resigns the complexity, noise, variability inherent in EOG signals. Addressing these challenges required the advanced model for the capable of dynamically refine and selecting relevant features at the multiple scales, while the minimizing the computational overhead to ensure the real-time compatibility. Most existing methods has been evaluated in a large-scale datasets with the limited subjects and conditions. But the comparison using the public data sets is required to establish the reliable benchmark for evaluating EOG-based models. Models can achieve the higher accuracy, robustness, generalization of across diverse conditions and subjects. EOG data is a high dimensional containing a mixture of useful signals, components, and irrelevant redundant of information. So the processing for all the features simultaneously can computationally expansive and may lead to over fitting to the poor generalization. So the research methodology for the selected paper is to the introduction for the self-calibrated conventional layers, that adaptability for the adjustment of process-based, conventional process-based input features for the novel approach. This model help that proposed model, which is RSCA, which is Reducible Self-Calibrated Conventional Networking. This model automatically reduces the process-based feature inputs and noise and irrelevant information into the EOC signals, which are often noisy and variable, where they have a different variables in it. By the featuring of calibrating featuring extractions, the model become more robust to signal noise, improving the overall accuracy of eye movement classification without requiring a mutual processing step for the noisy removal. There is a two sub models and blocks and modules are in a main component into the RSCA network. The use of hierarchical residual connections with this multi-scale features extraction is a framework with a good architecture design. These residual connections ensure that the important level of the features are preserved throughout the network, even as the deeper or more abstract features are extracted. Each block contains the four branches and the framework that contain the self-calibrated convolutions. Self-calibrated CC convolutions have enhances the traditional convocational layers of splitting into the multiple channels, applying the both original and reduced scales for the combining them the refined output. This architecture enables the model to capture a broader range of eye movement characteristic by processing the information at multiple scale, while retaining the essential details might otherwise be lost into the deeper layers of the connections. These hierarchical residual structure allow more flexible structures into the scale features extractions compared to the single scale CNNs. The multi-scale connections, channel attentions, is the module for the development for the dynamically adjustment attentions for the different features in channels. The combination of local and global channel contacts are ensures that the model are not only focuses on the individual channel but also capture the overall channel dependencies. This allow the network to prioritize the most information and the informative channels as well. That suppresses the irrelevant and redundant features significantly the classification of eye movement as well. The attention mechanism adapt the variability of EOG signals that leading to the more accurate predictions across the different subject and conditions. Another branch captures the small scale localized features. These branches generate the attention's weight for the each feature map based on the relevancy of the feature map before the classification. This is the diagram which illustrates the architecture of reducible self-calibrated network with multi-scale channel attention. which is used in EOG-based eye movement classification. This shows how the network processing input data is extracted with a multi-scale applies channel attention mechanism and also perform the final classification as well. Let's break down. This is the input. The input is typically the EOG signal, which is split into the multiple parallel processing stream for the multi-scale feature extensions, like three extensions. Here is a HRSC block in depth, with each block include the SOC convolution, RELU, and the max pool. The SEC is basically specified for the convolutional operations, help the network dynamically adopt the input features, which enhances the features learning by mitigating the impact of noise and irrelevant information. The RELU is basically the function to introduce the non-linearity, enabling the network model to the complex relationship. However, the max pool, which reduces the dimensions of feature map, retaining only the most information, which allow the processing into the multiple scale and also increasing the computational efficiency as well. It contains two blocks: local channel context aggregator and global channel context aggregator, which is the local channel, which focuses on extracting information from each individual channel by capturing the local dependencies, while the other hand, the global channel contact, which focuses on global dependencies, allow the network to aggregate the information from all the channels and capture the all over the context. Then those aggregate work together and decide to which channel are more important by assigning the attention weight, and then the broadcasting by sigmoid is occur, which combines the output into the local and global channel contact by adding them and allowing the network to merge their contributions. There is the two layers, which is FC and softmax layer, which is the refined features to pass through towards the output. The FC layer is basically fully connected layer that consolidates the information from the features of the map for the final classification. While the softmax layer is the function which is used to assign the probability to the different classes which lead the final prediction. These are the data sets used for the evaluation. Researcher take the 5 different data sets in this study, which is contains the different variety of the eye movements such as up, down, left, right, blink, fixation as well. And also there is a number of electrodes from the different subjects. In the data set, there is a diversity of different movements, which ensures that the network, reducible self-calibrated network, have a different tested across to the real world scenarios. Experimental setup is contained on cross validation with the LOSO function. LOSO cross validation is basically the one subject's data is left out for the testing while the rest are used for the training. This ensures that the model performance is generalized all over the individual or all over the dataset one by one. There is the results that shows into the two diagram. The first diagram shows the combination of HR, SC and MSCA, which is the orange bar, and their results lies between 90.5% to 96.9%. On the other hand, on the right side, there is a diagram which shows the vanilla and convocation and a self-calibrated convocation, which tells us about the gray bar represent the vanilla convocation and the orange bar represent the self calibrated convocation. and their results are a lie in between, probably from 90% to 6% of SCC, which is a self-calibrated, and vanilla will lie between 89.4% to 96.4%.